Hey guys, we're well on our way in this chapter, going to 2.4 today with just chain rule. You can see that awesome picture at the top. So I want you to think about that. It's just not a fun picture for fun. I want you to think of these chain links as being all connectors, and we're going to tie that in. It's called the chain rule, and that totally makes sense with what we're learning. So today we're going to learn how to find the derivative of some functions that we couldn't before. So kind of cool. Chain rules are used to differentiate composite functions. So what's a composite function? We've been looking at them already. Composite functions are obtained by substituting one function into another. An example is f of g of x. You also see it written like this sometimes with this circle. Looks like the word fog. That's really a tiny circle. Okay, so when you have composition of functions, you have an inside and an outside. So I'm going to use that a lot today. I'm also using a ton of highlighters if you want to grab some of those. Okay, so we're first going to look at functions and just say, well, do I know what the inside is? Do I know what the outside is? So if you look here, can you see g is the inside? So g gets put into the function f. I want you to look at a and look at 2x minus 4 to the fifth and say, what is the inside? Can you see that 2x minus 4 is your inside? We're going to call the inside g of x. So g of x is matching up with this 2x minus 4. Look over in the first column. I'm asking you for g of x. And I'm asking you to replace g of x with what the inside is. So I'm going to say that u is 2x minus 4. Okay? So we have the inside. Now we have to find the function that we are going to substitute 2x minus 4 into. So the outside function, if you will. Well, if you look back over here again, g goes into some function f. So 2x minus 4 went into some function, which is raised to the fifth. So if I can imagine replacing this 2x minus 4, see how it's u? I'm going to, instead of writing a 2x minus 4 here, I can call it u. So my overarching function, my outside function, is going to be u to the fifth. Okay, now looking at it, let's make sure it makes sense. If u is 2x minus 4, I can replace this u with 2x minus 4. So I'd get 2x minus 4 to the fifth, which is exactly what we started with. Okay, we saw something like this before, and I asked you when you have something like this to rewrite it as sine x all squared. This is really going to help you on this section. Okay, so this is why I was having you do this before. Now that you have that, you can see your inside stuff. Okay, we're using pink here. Let's stick with it. The inside is u equals sine x. If I have u equal to sine of x, I can now replace sine x with u, and I'm going to get u squared as my overarching function. Okay, so identifying these is key to moving on in chain rule. Okay, look on the left. We've been able to do this stuff so far. If I want to take the derivative of this function, it's 2x. The derivative of this function is cosine, and the derivative of this is 3. Those are all kind of boring, nothing too fancy. Look to the right now, and it picks up a little bit. Wouldn't we rewrite this to be x squared minus 1 to the half? We like doing that, so we can have fractional exponents instead of that radical. Now, I need you to know that the derivative here is not 1/2 x squared minus 1 to the negative half. Over here on the left, we just had an x raised to 2, and we could apply the power rule. Over here, we have all of this raised to the half, and we need to learn chain rule now. Okay, this next one, this is not cosine of 5x. Look to the left. This was just an x. Now we have a 5x, so that's totally different. Same thing here. You can probably guess what I'm going to say. This derivative is not 3x minus 2 to the 6. So when you have something on the inside that is more than just an x, we got to use chain rule. Okay, so what is chain rule? What this says is if y equals f of u is a differentiable function of u. Okay, if we know that, look up above. Do you guys see right here how I'm referring to this as u? Okay, the next one, if u equals g of x is a differentiable function of x, then f of g of x is a differentiable function of x, and the composition occurs. Okay, so another way to say this I've written down below, so let's look there. just reminding you of a couple things. If you look at this first part, so we're used to this dy dx, that means derivative. We almost always have x and y in our functions. But this thing is new, dy du and du dx. So let me just tell you what those mean. Du dx is the derivative, I'm going to use shorthand here, of u with respect to x. And then what's the other one we have to look at? dy du is the derivative of y with respect to u. So look at derivative of y with respect to u, derivative of u with respect to x, derivative of y with respect to x. Okay, so if you look at this, can you see that this part, which is y is a function of u, so dy du, so that matches up. And then the next part, they say g, which is u is a function of x. Okay, and then look at du dx. Now, if you're looking at these, can you guys see that those are gone? And that's how you're left with dy dx equals dy dx. So what all of that was about is our goal is to get dy dx. That's what the question's going to ask for. In order to do that, because we have composition of functions, we are going to say dy du, and then we're going to do du dx. And these keep linking, and we're left with the two things that we want. Again, this will make so much more sense once we keep going. So what you're going to do on the right, if you're asked to take the derivative of a function that's a composition, you are going to take the derivative of the outside first. Okay, notice that I only applied the derivative to f. G is along for the ride. Okay, but g is in the middle, right here, and then we have to take that derivative. So that's kind of how the chain links comes in. So right here, we take the derivative of the outside, g's along for the ride, but then I take the derivative of g to get g prime. And then look, I could look in the parentheses again. What's the derivative of x? It's 1, and we totally don't need to write that. So let me say that one more time. If you have f of g of x, you take the derivative of the outside, which is f prime, and I write that. G is along for the ride. Now I still need to take g's derivative, so now I take g's derivative, and I get g prime. I still have parentheses, but I don't need to think of it that way because the derivative is just 1. So we've kind of been using chain rule this whole time. Look up here. If I took the derivative of this, right, the derivative is 3 and the derivative of x is 1, if you think of it that way. The derivative here, the derivative of sine is cosine and the derivative of x is 1. We just haven't been writing it. Okay, let's try some problems. After you see some problems, you might want to go back and look at this again. It might make more sense. Now look at the first one. This is totally fine. We don't need chain rule. Let's do this the old way. To do it the old way, we would expand. So you're going to get 4x squared minus 12x plus 9. Notice I did not write y prime because I did not take the derivative yet. So then y prime is 8x minus 12. Okay, fine, easy. Let's write dy dx for no reason other than we are using that notation above. Okay, now let's use the new way. So the new way, I'm going to write dy dx, know that y prime is totally fine. Find the inside stuff and let's highlight it. I'm going to pretend that that whole inside stuff is just the letter u. So if I had u squared, what is that's derivative? Isn't it 2u? So we are going to pretend, again, look up here. When we did this, we took the derivative of the outside and got f prime, and g is along for the ride. Okay, we'll deal with g in a second. So here is g on the inside. Okay, we're going to pretend this is one thing. So what's the derivative of u squared? It would just be 2u. But u is 2x minus 3. If you take the derivative of this, it's 1, and it's there. Now, because that's our inside, we now have to take that derivative. And what's the derivative of the inside? And you end up with 2. So here is the new thing. If you clean it up, you are going to get 2x minus 3. We like things factored, but just to match them up, 8x minus 12. Anyone notice anything awesome? These guys are the same. So woohoo, because we know how to do it the old way, now this new way is matching. Think about it like it says underneath as unpacking boxes. You start on the outside and you keep working your way in. Okay, this is important, this next bold thing too. You want to rewrite so you can see the inside and outside. So parentheses are key. Let me go back up here though and point something out. Now this old way was fine because that was to the second power, right? Foiling, we love that, no big deal. What if this was to the 10th power? Do you get that we would not want to do this way and we would want to take this awesome shortcut? So even though it didn't matter in that problem, it totally will in the future. Okay, going on to the next one. So do you guys see why this is chain rule? It's because the stuff on the inside is not just one letter. What I mean by that is if I had x to the 3/4, totally fine. But look at this one. It's not x to the 3/4. It's 7x minus 5. Notice that operator out in front, d over dx. It's saying, hey guys, take the derivative. Okay, let's pretend this inside is just one thing. So it's going to be 3/4 of that thing to the negative 1/4 times the derivative of the inside, which is right here, which is 7. You cannot leave that out. It's a common mistake. So now when we rewrite it, we're going to get 21 over 4. And then remember, we don't want negative exponents, so let's rewrite that as the 4th root of 7x minus 5. Not too bad. It's just easy to be a little forgetful on these and forget the inside, but you guys are going to do great. Let's rewrite this. Now the operator is dt, d dt, because we have a t. So let's rewrite this as 5 minus t to the negative 1. So we could totally use a quotient rule here, but I think this is a lot easier to rewrite it as the whole bottom to the negative 1. Okay, again, this is not just t to the negative 1, which is easy. We have all this stuff inside. This is a red flag saying, hey, let's use chain rule. Bring the negative down in front. The yellows along for the ride, decrease the power by 1. Now, take the derivative of the stuff on the inside, which is negative 1, giving you 1 over 5 minus t squared. Okay, hopefully this is going well. Now we have d dx, because we have an x squared. We are going to rewrite this. Remember, we don't want to use radicals. We want to rewrite it as x squared minus 1 to the half. Clearly chain rule, this stuff inside, if it wasn't chain rule, it would be x to the half. But we have a whole bunch of stuff. So when we rewrite it, we bring the half down. We treat the yellow as though it's not even there. We just write it over. Decrease your power by 1. Now multiply by the derivative of the yellow. The derivative of the yellow is 2x. Cleaning this up, you can see these 2's cancel, and I'm left with x over the square root of x squared minus 1. Okay, again, chain rule, really not bad. We just have to remember the inside. Oh, look, they're picking up. Okay, let me point something else out also. I mentioned here, it's really important that you rewrite them. Okay, rewriting is really helpful. We did it a couple times. We did it here when we had the bottom to the negative 1 to avoid quotient. We did it here when we had a radical. Okay, we're going to have to rewrite it again. I see a radical. So let's rewrite this as d dx. Oh, do you guys see this has a whole bunch of inside stuff? And this is going to be 2x plus 1 to the 8th plus 4x all to the half. Oh, geez. Okay, double highlighting here. Now, I'm going to highlight all of this. This is the all inside. I want you to notice that this 1/2 is the outside function. So we are going to treat the inside as though it's all together. And actually, I'm going to start all the way on the left and erase this equal sign because I bet I have to write small. So pretending the yellow is 1 unit, I write 1/2. I bring the inside stuff down, which is 2x plus 1. I'm sorry, I rewrite the inside stuff. I brought the 1/2 down. Let's make sure my parentheses are good. Okay, so going over this, you bring the 1/2 down in front, you rewrite this inside, and you decrease that power by 1, giving you negative half. Now, whatever I have highlighted in yellow, I now need to take that derivative. Okay, so let's go over this part slowly. I'm going to have another inside. So I am going to bring the 8 down. Okay, so we're going to go ahead and write that 8. And then I'm treating the blue as one term, so I copy it over without thinking, and I decrease the power by 1. Now I need to take the derivative of the blue, which is 2. You might want to pause and go back and watch that again. plus the derivative of 4x is 4. Okay, this problem sure did kick it up a lot. Okay, now look, we have a couple things being multiplied, so it's not as bad as it looks. See these parentheses, all this stuff, and then these parentheses is all this stuff. So what we're really going to do is sort. So we're going to put this 1/2, that 2 goes on the bottom, as does all of this stuff. The negative 1/2 power means the square root on the bottom, so that's 2x plus 1 to the 8th plus 4x. This stuff on the right now, right here, can go all in the numerator, so it's going to be 16, 2x plus 1 to the 7th plus 4. Okay, again, if you need to go back and rewatch that, go ahead. Now look at these terms. See the plus sign here separating? So I have this term, and this whole thing on the bottom. Notice that a 2 can go into all of that. I'm going to go ahead and simplify that, and I'm going to get 8, 2x plus 1 to the 7th plus 2 all over the square root, 2x plus 1 to the 8th plus 4x. Okay. It's not going to get much worse than that. Next one. Ooh, maybe I spoke too soon. We'll see. Okay, looking at this one, let's take the derivative and let's rewrite this. Let's rewrite this as x cubed over x to the 5th plus 4 to the half. Okay, now that we have this, we can look at this and see what rules we need. We know we need chain because we have something inside raised to a power. We also have quotient because we are dividing. Okay, so going forward on this, what we're going to do is use quotient. Low d high is the beginning. So low d high is the derivative of the top, which is 3x squared. Hey, no chain rule up top because look at an x, just one thing. Okay, minus high d low, high. Now when I take the derivative of the bottom, we are going to use chain rule because we have something other than an x raised to a power. So chain rule here is going to be 1/2. You have x to the 5th plus 4 to the negative half. Notice this yellow stuff was the inside. I now need that derivative, which is 5x to the 4th. All over low, so square the bottom and you get x to the 5th plus 4. Okay, in the next step, you can clean things up and then factor. I'm going to go right to factoring. I want you guys to notice here that we have this minus sign dividing everything, not dividing by divide, but splitting into 2. So I have this term here and I have this term here. Okay, I'm going to do the easy stuff first. I have a 3 here and a 5 here. Nothing factors like that, but I do have a half. So let's factor that half out. Also, I have an x squared and an x to the 4th. So I'm going to start by taking out 1/2 x squared. Here's where the factoring gets messy. I also have an x to the 5th plus 4 and an x to the 5th plus 4. I'm going to look at exponents. You always want to take the smallest one. What's smaller, a half or a negative half? You got it, a negative half. So that is going to be x to the 5th plus 4 to the negative half. We've taken out everything we can. Now we're going to write what's left. Look on the left piece. So this. Look, I took out this x squared, that's gone. I took out a half. So a 3 divided by a half is 6. Also, this next step, I have an x to the half, and I took out a negative half. So what that looks like, guys, I'm just going to use an easier variable. If I have x to the half and I took out a negative half, that really is like multiplying because it's a negative in the bottom and you get 1. And you're going to get so good at this. So if I have a half and I took out a negative half, this is what it really looks like. And you really end up with x to the 1. So this is going to be x to the 5th plus 4. Minus, and this is that pink minus, right, that matches up there. So now I'm looking over to the right. I took out a half, so that's gone. I have a 5 left, okay, so I'm going to write the 5. Let's go back to what we took off. We also took out an x squared. I have an x cubed and an x to the 4th, which is x to the 7th, so now I'm left with an x to the 5th. Also, I took out this whole thing. Woo, we need a break. It's all out, so that's it, and I'm going to close that off. The denominator is x to the 5th plus 4. Now our job is to rewrite this. We don't want complex fractions. So do you guys see this half here? Instead of multiplying by a half, we can just write it as a half and write 1 over 2. The x squared, which is right here, stays. So now I've taken care of that and that. This needs to go on the bottom. So I'm going to write an x squared on the top, and I'm going to write the square root of x to the 5th plus 4 on the bottom. Now the stuff inside, let's go ahead and distribute. I'm going to have 6 go there, and then a minus that at the end. So I am going to have a 6x to the 5th plus 24 minus 5x to the 5th. On the bottom, I also have an x to the 5th plus 4. Let's take a sec, make sure this looks beautiful, and it does. Last step, I have an x squared. If you combine like terms in here, this gives me 1x to the 5th. So I have an x to the 5th plus 24, all over 2. Now do you guys see here that this inside is the same? This is really raised to the first. This is a half. So a half plus 1 is 1.5, which is 3.3 over 2. So this is going to be x to the 5th plus 4 to the 3 halves. 3 halves is 1.5, and I have a 1 and a 0.5. Okay, I hope you're proud of yourself after that one. Look at this. Look how fancy that looks, and you guys did it. Okay, let's go on to 4. So chain rule gets messy, be careful. Find the domain of this. Okay, so to find the domain of this, we're just going to look in the denominator. Remember, you can't have the denominator equal to 0, so x can't be a half. So you can write domain a couple of different ways. One way is we can say we want all x, but x can't be a half. Done. Domain is done. Going on. Show that the slope of every line tangent to the curve is positive. Well, guys, you know what this means. What does it mean if they say the slope of the line tangent? We are for sure thinking derivative. Okay, so we want to show that the slope of every line tangent to the curve is positive. So what are they really saying? Aren't they saying show that f prime is positive? Okay, well, how about we start by finding f prime? We know f of x, we can rewrite this, remember, as 1 minus 2x to the negative third. It avoids quotient rule, and there's nothing in the numerator. So now when we go to take the derivative, for sure chain rule, because the stuff inside is not just one unit. Go ahead and bring the negative 3 down. You have 1 minus 2x to the negative 4. The stuff inside, we wrote it. It's like along for the ride, but we can't forget about it. And then that derivative is negative 2. If you clean this up, you're going to get 6 over 1 minus 2x to the 4. So yeah, we're finding the derivative, but why were we doing this? We had to imply what they were saying. They said show that the slope of every line tangent, which means derivative, so show that the slope is always positive. Well, is this true? Look at the 4th. Isn't that always going to be 0 or positive? And 6 is always positive. So sure, this is guaranteed to be positive, but remember, x can't be a half. So we're going to say for all x except x equals a half, the derivative is positive. Okay, we did what they said. Now we have to find a conclusion. Well, what does a positive derivative mean? Think about positive if you have a positive slope. Isn't this a line with a positive slope? What is the function doing as you move from left to right? It's increasing. So what could we say here? We could say f is increasing. We're doing this because they asked us to make this extra conclusion. For all x except, do you remember our issue? When x was a half, because that gave us a 0 in the denominator. Okay, this was like an application and a chain rule. So this is, this goes with the first day. I'm going to stop right here, and I'll pick up later. See you on day 2.